In my left hand I have the original breadboard prototype and in my right hand the finished PCB. In this video I'm going to show you how I went from a breadboard design to a fully functional PCB. Everything started with a simple idea. I wanted to build an LED chaser as a demonstration circuit. Instead of an Arduino Uno, I used an ATmega 328P, which is basically the chip of the Arduino Uno. I also needed a crystal with a few capacitors and resistors. At this stage, the microcontroller is still connected to the Arduino Uno, but this is only for power supply, because I need 5 volts for the chip. Before anything could work, I had to burn the bootloader. This step is essential because it tells the ATmega how to behave like an Arduino. After burning the bootloader, I uploaded my LED chaser program. Everything worked perfectly, just like a normal Arduino. But the LEDs were still missing, so I connected them and added the rotary encoder so I could control the speed of the lights. The important thing here is not the specific components, but that the circuit works reliably on the breadboard before you even think about designing a PCB. Next, I opened KiCad and started drawing the schematic. I added the ATmega and the other components. I also added all the power connections and a voltage regulator that turns 9 volts into a stable 5 volts. Then I ran the electrical rules check. I immediately got an error message saying that the power input was not driven by any output. After some research, I learned that I had to place a power flag, which tells KiCad that the circuit actually receives power in the first place. After adding the power flag, the error disappeared and the schematic was finished. The next step was assigning footprints. KiCad already includes many standard footprints in its database. However, sometimes you cannot find the exact component you are using. At that time I honestly did not know which footprints to choose, so I measured my components and selected footprints which roughly matching dimensions. Some were larger than necessary like the crystal, but the pin spacing was correct, which is what really matters. Now comes the fun part. Designing the actual PCB layout. You can import all symbols automatically by pressing a button. The program helps you by showing which pins must be connected and warns you if something is missing. While placing components, I also arranged everything neatly so the board looks clean and the components have enough space between them for proper soldering. I also changed the board settings from 4 layers to 2 layers because I only needed a simple board. The PCB turned out way better than I thought. After that, I made some final refinements and performed the necessary design checks to make sure everything was correct. Now I created the Gerber files and uploaded them to a PCB manufacturer and I ordered the boards. I chose GLC PCB because it's very cheap and also reliable. I also chose a blue solder mask because it looks nice. The total cost was about $4, including shipping, although delivery took about 11 days. When the package arrived, I was honestly quite excited. Inside were 5 professionally manufactured PCBs. The quality was surprisingly high, even better than some commercial kits I've built before. I did notice one small mistake. I wanted the production number where the GLC label was, but I forgot to set this when I was ordering, but it's not a big problem. The final step was soldering the components. I reused the same parts from the breadboard. I did not have proper screw terminal for the power input, so I simply soldered the power wires directly to the board. And then came the moment of truth. I connected a 9-volt battery and powered it on. And surprisingly, it worked immediately on the first try. So that's the general workflow going from a breadboard prototype to a finished PCB. I hope you found this process interesting. If you did, please like and subscribe. All the best and see you in the next video.